In episode 48, titled Load Balancing Basics, Global versus Local and What VIP means, the focus is on load balancing as the practical mechanism for distributing work across resources so that a service can scale and stay available under stress. Load balancing shows up everywhere in modern architectures, but the exam tends to test the foundational assumptions rather than vendor-specific details. You need to understand what problem is being solved, what a stable client-facing address represents, and how scope changes the role of the balancer. When the test asks you to choose global or local balancing, it is really asking you to identify the failure domains you are designing around and how users reach the service. When it asks about a virtual Internet Protocol address, it is testing whether you understand the difference between an interface address on a server and an address that represents a service as a whole. If you keep those ideas straight, load balancing questions become predictable instead of tricky. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. Load balancing starts with a simple concept. Instead of sending all client requests to one resource, you distribute requests across multiple resources that can each handle the same kind of work. The resources might be servers, instances, containers, or service endpoints, but the common requirement is that they can all serve the same function for the client. Distribution spreads load, reduces the chance that any single resource becomes overwhelmed, and improves availability because if one resource fails, others can continue serving requests. Load balancing also becomes the control point where traffic is managed, including which targets are eligible, how decisions are made, and how failures are handled. The exam often frames this in plain language, such as, how do we ensure requests are spread across multiple servers? But the real expectation is that you recognize load balancing as a service-level capability, not just a network trick. A good load balancing design also assumes that the balancer itself must be reliable and observable, because it becomes part of the service path. A key concept in load balancing is the virtual Internet Protocol address, which is a stable address that clients use consistently to reach the service. Virtual here means the address represents the service and the balancer, not a specific backend server's network interface. Clients connect to the virtual Internet Protocol address, and the balancer then selects a backend target to handle the request, allowing backend membership to change without breaking client connectivity. This stability matters because scaling events, failures, and maintenance change which backends are available, but clients should not have to know those details. The virtual Internet Protocol address also provides a single logical entry point where policies such as transport layer security termination, connection limits, and health-based steering can be enforced. On the exam, virtual Internet Protocol address questions often test whether you understand that the client talks to a consistent front door even when the backends behind it change. If a scenario describes clients connecting to multiple backend addresses directly, that is often a sign that the design lacks a stable service entry point. Local balancing is load balancing within one site or one region, and it is the most common pattern for scaling a tier inside a defined failure domain. Local balancing focuses on distributing requests across multiple targets that are close to each other in network terms, such as multiple instances in the same data center or region. The goals are typically capacity and availability within that scope, ensuring that a failure of one instance does not interrupt the service and that the tier can handle peaks by adding or removing targets. Local balancing is often paired with auto-scaling and metrics, because the set of targets can expand and contract based on demand. In cloud environments, local balancing is usually the baseline for web tiers and application tiers because it provides a clean way to scale horizontally. The exam tends to test local balancing when the scenario describes one region and multiple instances that must share traffic. The important point is that local balancing assumes users are already reaching the site or region, and the balancer decides which internal target serves each request. Global balancing is load balancing across regions, and its primary value is resilience and latency optimization at a larger geographic scope. Global balancing can direct users to different regions based on proximity, performance, or health, helping users reach the nearest healthy region and reducing round-trip time. It also supports resilience because if one region fails or degrades, global balancing can steer users to another region that remains available. This is a higher-level decision than local balancing because the choice is not between instances in one site, but between entire regional deployments with their own independent infrastructure. Global balancing often relies on mechanisms like domain name system-based routing or Anycast, but the exam usually cares more about the design intent than the specific technique. The key is that global balancing changes the failure domain you are addressing, moving from instance or zone failures to region-level disruptions and latency concerns. When a scenario talks about users worldwide, regional outages, or directing traffic based on location, global balancing is usually what is being tested. Health checks are the foundation that makes load balancing trustworthy, because without health awareness, the balancer would continue sending traffic to failed targets. A health check is a periodic probe that verifies whether a target can accept and process requests, and it can be as simple as a connectivity test, or as complex as an application-level request that confirms real functionality. When a target fails health checks, the balancer removes it from the eligible pool automatically, which reduces downtime and prevents repeated user errors. Health checks also support safe deployments, because new targets can be added and verified before receiving production traffic, and unhealthy targets can be drained out of service without manual intervention. The exam frequently expects you to understand that health checks are not optional decoration, but the mechanism that enables automatic removal of failed targets. If a design lacks health checks, it tends to rely on luck and manual response, which rarely meets availability expectations. Health checks are also only as good as what they test, so shallow checks can pass even when the application is failing, which is a common real-world trap. Distribution methods describe how the balancer chooses targets, and they often map to different goals, such as even load, least work, or weighted control. Even load methods aim to spread requests uniformly, which is often expressed as round-robin or similar approaches, where each target receives a similar share over time. Least work methods attempt to send new requests to the target that is currently handling the fewest active connections or has the lowest measured load, which can improve responsiveness when request durations vary. Weighted methods allow certain targets to receive more or less traffic intentionally, which is useful when targets have different capacity or when you want controlled migration during deployments. The exam may present these methods as choices and ask which one best matches a scenario, and the right answer depends on what the scenario values, such as fairness, performance under variable load, or gradual rollout. The important concept is that distribution is not random, and the method should align with the nature of the workload and the capacity of targets. When you can explain why a method fits a goal, you are operating at the level the exam is testing. A straightforward local balancing scenario is a web tier spread across 3 instances, where you want to distribute incoming requests so no single instance is overloaded, and the service stays available if one instance fails. Clients connect to the virtual Internet Protocol address, the balancer checks health status, and then it sends each new request to one of the healthy instances based on the chosen distribution method. If one instance becomes unhealthy, health checks detect it, and traffic is automatically shifted to the remaining 2 instances. This scenario illustrates why the virtual Internet Protocol address matters, because the client never needs to know that the backend membership changed. It also illustrates why health checks matter, because without them, the balancer might keep sending requests to a failed instance, creating unnecessary errors. In practice, this pattern is often paired with autoscaling so that the 3 instances can become 5 under load, or become 2 during low demand, but the load balancing logic remains stable. On the exam, when you see 3 instances behind a balancer, you are expected to reason about health checks and distribution choices within one scope. A global balancing scenario is steering users to the nearest healthy region, which combines latency optimization with resilience. Users in one geographic area should ideally reach the region closest to them to reduce latency, but if that region is unhealthy, the system must send them elsewhere. Global balancing can accomplish this by evaluating region health and user location signals, then directing the user's connection to the best region available at that moment. Once the user reaches a region, local balancing typically distributes requests across instances within that region, which means global and local balancing often work together. This layered model is important for exam reasoning because global balancing does not replace local balancing. It complements it at a higher scope. When one region fails, global balancing should shift traffic, but the surviving region must have enough capacity to handle the increased demand, which brings availability and capacity planning back into the picture. The exam may describe a regional outage and ask what mechanism ensures continued access, and global balancing is often central to the correct answer. Session state is one of the most common issues that makes load balancing behave badly from a user perspective, especially when it breaks logins or causes users to lose continuity. If the application stores session state on a specific backend instance, then distributing a user's requests across multiple instances can cause the application to treat each request as a new session. This can result in repeated login prompts, lost shopping carts, or inconsistent authorization behavior, all of which look like reliability failures even though the infrastructure is technically healthy. Some load balancers support session persistence, which keeps a user's requests on the same backend, but that can reduce effective load distribution and complicate scaling. A more robust pattern is to externalize session state into a shared store so that any backend can serve any request, but that requires deliberate application design. The exam tests whether you recognize that load balancing assumes a certain application behavior, and that assumption must be validated. When you see users are being logged out after enabling a load balancer, session state is often the real issue. Another pitfall is letting the load balancer become a new failure point, which can happen when the balancer itself lacks redundancy or when the design assumes the balancer cannot fail. Because clients depend on the virtual Internet Protocol address, a failure of the balancer or its front end can look like total service failure even if all backends are healthy. High availability for the balancer may involve redundant instances of the balancer, managed load balancing services that provide built-in resilience, or designs where the virtual Internet Protocol address can fail over automatically. The exam often includes distractors that add redundant backends but ignore balancer redundancy, which reveals a misunderstanding of where the single point of failure moved. You should treat the load balancer as part of the service, subject to the same availability expectations as the backends. Redundancy at one layer does not compensate for a single point of failure at another layer. When you see single balancer, your instinct should be to ask how it stays available. Quick wins often come from pairing load balancing with autoscaling and good metrics, because distribution alone does not solve capacity and visibility problems. Autoscaling allows the pool of targets to grow when demand increases and shrink when demand decreases, making the load balancer more effective because it has the right number of healthy targets to choose from. Good metrics allow you to understand whether the balancing method is achieving its goals and whether health checks are detecting real failures rather than producing false positives. Metrics such as response time, error rates, target saturation, and connection counts help you tune health thresholds and distribution strategies. These quick wins also support incident response because they provide evidence about whether problems are caused by insufficient capacity, unhealthy targets, or misrouted traffic. The exam often rewards answers that include monitoring and scaling because they show operational maturity rather than purely theoretical design. Load balancing is a control mechanism, and controls must be measured to be trusted. A useful memory anchor is VIP, health, method, scope, redundancy, because it captures the essentials that the exam expects you to understand. Virtual Internet Protocol address is the stable front door that clients use consistently. Health is the mechanism that removes failed targets automatically so traffic is not sent into a black hole. Method is how requests are distributed, whether evenly, by least work, or by weights aligned to capacity and rollout needs. Scope is whether the balancing decision is local within a site or region or global across regions for latency and resilience. Redundancy is the reminder that the balancer itself must not become the single failure point. When you can recite and explain this anchor, you can usually answer load balancing questions quickly and correctly. To apply the concept, imagine being given a scenario and asked to choose global or local balancing, and the right answer depends on what problem the scenario is trying to solve. If the scenario is about spreading load across multiple instances in one region and surviving instance failures, local balancing is the core requirement. If the scenario is about user latency across geographies or surviving a region outage, global balancing is required, often layered above local balancing within each region. You should also consider whether the application can tolerate requests being served by different backends, because session state concerns can affect whether persistence or shared state is needed. You should consider whether the balancer is redundant, because a single balancer can erase the benefits of redundant targets. The exam expects you to match the balancing scope to the failure domain and user distribution, not to default to one choice. When you answer, you should be able to state what scope is needed and why. To close episode 48, titled Load Balancing Basics, Global versus Local, and What VIP Means, the essentials are that load balancing distributes work across resources. Virtual Internet Protocol address provides a stable entry point, and health checks keep traffic away from failed targets automatically. Local balancing spreads requests within one site or region, supporting scale and availability within that scope, while global balancing steers users across regions for resilience and latency. Distribution methods like even load, least work, and weighted control are tools that align request steering with capacity and rollout goals. The pitfalls are predictable, including broken logins when session state is not designed for distributed backends, and new single points of failure when the balancer lacks redundancy. Pairing load balancing with auto-scaling, metrics, and monitoring turns it from a static traffic splitter into a reliable service control. Your rehearsal assignment is to narrate the virtual Internet Protocol address path from client to balancer to backend and back, stating what changes when the scope is local versus global, because that narration is the exact level of clarity the exam is built to test. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.